Hello students. Today we shall discuss something about Gauss theorem. But before stating the theorem, let us be aware of certain small things like area vector, then solid angle. What is meant by area vector? For the first time in this chapter, we are going to treat area as a vector. You can see this is the area we this is area vector and its direction is given by the outward drawn normal n cap. This is the direction of area vector and the length of the arrow gives the magnitude of the vector A. Area is treated as a vector here in this chapter because the orientation of area changes in the field. So we consider area as a vector, otherwise for the first time you are observing area as a vector. Then now what do you mean by solid angle? Have you seen a watermelon or a solid sphere or a spherical surface? Like this is a spherical surface, and if I say this is a small area ds, then at the center of this sphere you will see, if I join all the points of this area ds at the center O, then here you will see a small angle d omega will be made. So this is known as the solid angle. The angle subtended by this small surface element at the center of this sphere. This is known as the solid angle. And remember students, this area of the surface element ds, this is directly proportional to the square of the radius. That means ds upon r square is equal to constant, and this constant is d omega. This is actually d omega. If I talk about the entire surface of the sphere, means for whole of the surface, what is ds? Means integral of ds is s, this becomes s, this is 4 pi r square, or you can say omega means the total amount of solid angle made by whole of the surface of the sphere at the center. So that will be 4 pi r square upon r square. So this is 4 pi steradian. Steradian is the unit of solid angle, students. So this is what we call solid angle. And one more case I can take. Suppose for some angular position of the area, if I say like this, this is the area element, and you can say at a distance r from the center, and this area, this is giving its direction like this. This is, you can say dA, and this is n cap. So this is angle theta. If I say the projection of this area, this is the area dA, the projection of this area like this projection is ds or dA cos theta. The projection of this area will be dA cos theta, and if I say the sphere which is drawn taking O as center and R as the radius, if we draw a spherical surface, then on that sphere the projection of this area will be dA cos theta. So in this case, this is the solid angle d omega, and this d omega is dA cos theta upon r square. So this is the formula which you will have to remember, because we have to deal with the derivations which are going to come after this. So this is about the solid angle, and now we come to the topic electric flux. Please note down, students, what is electric flux. The total number of electric lines of force which are passing through unit area placed in the electric field, this is known as electric flux. Students, once again, the total number of electric lines of force which are passing through unit area which is placed in an electric field, held in an electric field, that is known as electric flux. Okay, the number of lines, the total number of lines of force. So this is what we call, this is what we call electric flux. Electric flux is denoted by the symbol phi E, and its formula in terms of vectors, that is written as vector E dot vector S, or complete formula becomes E S cos theta. This is the formula for electric flux. And now we shall consider different cases of electric flux. I hope you have understood this, and you have to remember this formula now, because you have to deal with this in the whole chapter. So now see and verify from different cases. This is one position, one orientation of area. This is second orientation, and this is third orientation. You can see these are the electric lines of force which are passing through the area. These are the electric lines of force. This is the area S. Okay. Now you can see, I told you the direction of the area vector is given by the outward drawn normal n cap. Here in this case I will be drawing like this, n cap, and in this case I will be drawing like this, n cap. Here you can see the angle theta between n cap and the field lines. So this one first case, easily you can see, this is just like, these are the lines of force, and this is the coin which I am holding in my hand. Now you can see, if I hold like this, maximum number of lines of force will cross this coin. Okay. If I change the orientation of this area now, if I keep the area like this, then minimum number of lines of force will cross. Okay. And if I change the orientation like this, then few lines will cross. So these are the different orientations, you can say. So this is, what is the angle between n cap and E? Angle between n cap and E is theta equal to 0 degree in this case, theta equal to 90 degree in this case, and this is a general case. So in this case phi E is maximum, in this case phi E is minimum. Okay. Now from the formula you can verify, since phi E equal to Es cos theta, now you place theta equal to 0, so this is Es cos 0 degree, so this turns out to be Es, this is maximum. You can see, without using the formula, just now we had verified, if I place the coin like this, if I place the area like this in the field, then maximum number of lines of force will cross the area. And from the formula also we have verified this. And from here, this now, in this case, second case also you can see phi E equal to ES cos 90 degree. So this is 0. This is the minimum case now. The minimum number of lines of force will cross the area. And third case you can see phi E turns out to be E. Actually we take one component of electric field because whole of the field lines are not associated with whole of the area. So we take one component E cos theta with S, or you can take one component of area S, one component of area S cos theta with E. So that will turn out to be Es cos theta, and this is the complete formula for electric flux. So students, this is what we call electric flux, and we shall be dealing with this phi E in the whole chapter. I hope you have followed, and now we come to the next topic, which is very important, and that is Gauss theorem. So you write now Gauss theorem. As the name says, according to the name of the scientist Carl Friedrich Gauss, the theorem is known as Gauss theorem. Gauss theorem states that, you can write the statement, the total amount of electric flux emanating from a closed surface is given by the net charge enclosed by the surface divided by epsilon naught. Phi E is equal to sigma q upon epsilon naught. Once again, the statement of Gauss theorem. Gauss theorem states that the total amount of electric flux emanating, means or passing through a closed surface, is given by the net charge enclosed by the surface divided by epsilon naught. This is Gauss theorem. Phi E equal to sigma q upon epsilon naught. And now you have to prove this. This question comes in the board exams. Weightage 3 marks. Proof case 1. Flux due to a charge placed at the center of a spherical shell, or sphere you can say. Flux due to a charge placed at the center of a spherical shell. This is a sphere, and at the center charge q is placed, and we have to see the flux which is coming out, means the electric lines of force which are coming out from the whole surface, that should be equal to q upon epsilon naught. This we have to show. So we consider elementary area ds like this. This is n cap, this is n cap, perpendicular to the area, and electric field lines are also perpendicular to the surface. So what is the angle between the two? Theta equal to 0 degree. This is r. Okay. So what is the small amount of flux which is coming out from this elementary area? Small amount of flux is, small amount of flux through ds is, this is d phi e equal to e ds cos 0 degree, means e ds. Okay, this is the small amount of flux. Therefore, for whole surface, phi e is equal to how much? I take for the whole surface integral, no? So that is e ds. This you can write, e is constant everywhere. So integral of ds, and that is es. So this is es. So phi equal to, what is the value of E now? 1 by 4 pi epsilon naught q upon r square. This is the electric field. And what is S for the sphere? Surface area is 4 pi r square. So 4 pi cancels out, r square cancels out. Or you can say phi, you see, this is q upon epsilon naught, hence proved. This is the proof of Gauss theorem, and this is the first case I have taken, flux due to a charge placed at the center of a spherical shell. Now I shall take the second case, which says flux due to the charge which is not placed at the center of the spherical shell. Students, I hope you have understood this, and I shall take the second case now. Case 2, flux due to a charge not placed at the center of the spherical shell. That is understood. So once again I take the sphere, and now this is the center, but I keep the charge here, and we take the elementary area like this. This is ds, and you take, this is E. This is E and this is n cap, as I told you. So there is an angle theta, you can say now, between n cap and E, and of course this charge is at a distance r. So what is the flux through the small surface? ds. What is the flux through the small surface? ds. This is d phi E. This is equal to E ds cos theta. For whole surface, phi E equal to integral, surface integral of E ds cos theta. What is the value of E? 1 by 4 pi epsilon naught q upon r square into ds cos theta. You take it like this, q upon 4 pi epsilon naught, you take it out, and this is ds cos theta upon r square. So this is actually, this is d omega, and what is the value of d omega for the whole spherical surface? That is omega, which is 4 pi steradian. So this cancels out, and phi E, once again you can see, this is q upon epsilon naught. Once again proved when the charge was not placed at the centroles. So this is the proof of Gauss theorem. This is very important, and students, after this we have to take the applications of Gauss theorem, which you will see in my next lecture. I hope you all have followed this topic of Gauss theorem and flux, and now we shall see you in the next lecture. Goodbye.